Hi guys, so hopefully it's going to be the last unit of fluid. I'm going to look at fluid in motion, and I'm going to focus on Bernoulli equation and Bernoulli principle, as well as the equation of continuity. And as usual, it's really easy. I mean, it's not that hard if you understand the concept. So to do that, I just want to go back to what we have learned previously. Let's say you have a tank full of some kind of fluid, maybe water. So let's say it's water, right? And so here you have pressure P1. So it could be, for example, the atmospheric pressure. So here it could be the atmospheric pressure. And you want to know what's going to be the pressure here, right? And that pressure here, we call it P2. And of course, P2 is going to be greater than P1. Okay, so here at that level here, it's going to be P1. And let's say the height here is going to be delta H. So we have seen that delta P, which is actually P2 minus P1, equals rho. It's going to be rho, so that's going to be the density. So it's going to be rho G delta H. Okay, so I could rewrite the equation as the following. I could say P2, so let's say that's going to be H1 and that's going to be H2. Okay, so P2 minus P1 equals rho G, and I want everything to be positive on both sides, so I have H1 minus H2 because H1 is greater than H2. So all the terms with a subscript here of 2, I'm going to put that on one side. So P2 plus rho GH2 is going to be equals to P1 plus rho GH1. And you see, it looks very much like some kind of conservation law, right? And because it's like having before and then after. And if you remember from physics 1, remember the potential energy of a mass m in a gravitational field above some ground level is mgh, right? So just have to decide at which level of potential energy is 0, but that was the equation. Now, if we write potential energy, so it very much looks like this expression, right? Now, if you take the potential energy per unit volume, so you will have to divide by the volume. So then you get mgh divided by v. And we did that many times. You remember that the density, so here it's the density of water. If this is water, it's going to be density is the mass divided by the volume, right? So here we have mass divided by the volume. That's going to be rho GH. So these terms and these terms are actually energy per volume. This is also energy per volume, you know, because you have an equation. So you need to have the same units everywhere. So that expression here is actually the potential energy of the water per volume. Okay, because if you take a volume here of 1 meter by 1 meter by 1 meter, its potential energy is going to be rho gh, right? For one cubic meters, and here the potential energy will be less. So that expression is just the potential energy, and I should say the gravitational potential. So I should put a G here, gravitational potential energy per volume. So you see pressure, you can see that also as a energy per volume. it's kind of an internal energy, right? And you see that it's energy because if you have pressure, then you can apply a force over a distance, right? So it is a potential energy if it's nothing is happening here, but it has the potential to happen. If I make a hole here, you see the liquid is going to squirt out, right? That's because all that pressure here is doing work, and it's losing pressure, and of course here it's gaining kinetic energy. So all that pressure that you have here has the potential to turn into kinetic energy. So this is also a form of energy. So you can see that as, if you want to convince yourself that it has the unit of energy per volume, you could say that, remember that the pressure is a force per unit area. And if you multiply by a distance here, so I don't know, distance delta L, you multiply by delta L, the top and the bottom, so you can do that. You see, that's the dimension of work, so work is energy, and that's the dimension of volume. And it makes sense because, as I said here, if you put a hole here, all that pressure is going to do work on that liquid, pushing it out, and all that energy here is going to turn into kinetic energy. So this is the one form of Bernoulli equation, and it just shows you the conservation of energy. Okay, so let's take another example. So let's say now the liquid can flow, and we suppose that it's always the equation, the simple equation work only if you consider incompressible fluid. Okay, so it means the density is constant. It's not like a fluid you can compress or expand. And we also suppose that you have a steady flow and there is no turbulence. So it means it's flowing along a line like this, okay? So if it's flowing really fast, so you can make those lines close to each other. And if it's flowing slowly, those lines will be, farther apart from each other. These are called streamline. Okay, so let's remember an example we talked about when you have a straw. So what you have a straw here and you're drinking. Okay, and remember that if there is no atmosphere here, so if you put that straw in your mouth, okay, because you are drinking out of it. I'm very bad at making a drawing, but let's say you are trying to suck the liquid, maybe it's cranberry juice here. What's going to happen? It's going to have let's say a steady flow of cranberry juice, and you can drink it. Now it's happening because here, by sucking, you are making a vacuum. Okay, so you are taking the air in. So here you have the atmospheric pressure that is pushing here and doing work, and I'm going to call that P1 here. So you have P1 here, and here you're going to have some speed. Okay, the liquid is going to have speed, and the pressure here is going to be 0. Okay, and of course you're going to have height. So what's going to happen here, the pressure from the atmosphere is doing work on the fluid, gets pushing the fluid, so that here you're going to have the same pressure P1 here, because the level is all what matters. Okay, it's going to do work, that energy that you have here, that energy per volume P1 that you have here inside that straw at that level here is going to turn into potential energy, because you see it increases the height above the level, and it's going to also go into kinetic energy because the liquid is going in, you are drinking the liquid, okay, so it has some speed. So if you want to use the previous equation, you need to find a way to express the kinetic energy. So we have seen that you have potential energy per volume, which is rho gh, and we've seen that the pressure itself inside the liquid, so inside the liquid, because you remember the pressure is transmitted according to Pascal, so here you have some pressure inside it, okay, and that's a form of energy per volume. So now we need to find the kinetic energy per volume, okay, to make it everything consistent. And kinetic energy is 1/2 m. Now that's going to be, it's not the volume here, that will be the speed, and that's going to be the volume. Okay, so don't confuse the two V's, right? But the mass, so remember that density is mass divided by the volume. So mass is density times volume. So that's going to be equals to 1/2 rho, the volume, V squared divided by volume. So the kinetic energy per volume equals 1/2 rho V squared. Okay, so now I can use, and this is called the Bernoulli equation. It's just the conservation of energy. So it says that P plus your potential energy per volume plus your kinetic energy per volume equals constant if the liquid has no viscosity. So it means there is no friction happening, so you are not losing energy to heat, right? So I'm going to do the conservation of energy between here and there, okay? So I'm going to write P1. So I'm at that level here, I'm going to call that level 0. So H equals 0 here. And here that will be the level H. Okay, so P1 plus rho GH1 plus the kinetic energy, so 1/2 rho V1 square equals P2 plus rho GH2 plus 1/2 rho V2 square. So at that point, this is the atmospheric pressure, which is 10 to the 5, right? So I don't know, I'm going to put P atmospheric, which is 10, remember it's going to be 10 to the 5 Newton per meter square, plus, so the level here is 0, plus here the kinetic energy is 0 because here the fluid is not moving to begin with, so you start with no kinetic energy, and thanks to the work of that pressure the liquid is going to gain kinetic energy, and we suppose it's steady, okay, we don't as a whole it's a steady flow, equals, so inside the mouth you take you are moving the air, so you create a vacuum. Okay, that's why the atmospheric pressure is working. It can work up to 10 meters, by the way, remember that. So here you have 0, and then you have rho GH, and then you have 1/2 rho V squared. Yes, I just took that example because we talked about it last time. Okay, so then you have this example that the atmospheric pressure will be rho GH, that will be the height of your pipe. For example, here you can make a vacuum plus 1/2 rho V squared. This is just an example how to apply Bernoulli equation, and I'm going to give you even more examples. So another very nice example that I will also discuss later on is that if you have a tank for fishes, right? You just have a big aquarium. You know that it's impossible to move an aquarium, right? An aquarium is so heavy, you know, like if you need to empty your aquarium just to, let's say it doesn't have to be an aquarium, it could be a clogged sink, for example, and you need to remove the water. If you start to scoop out, it's going to take forever, right? So you all know what to do in that case, right? Let's say you have some fish here, you want to take the water, maybe not all the water, just remove some water, start to put fresh water inside. So what do? You're going to take a tube here, it's going to go up. I should have made it like a little bit more. Okay, let's see if I can move that. Oh. So you make a tube here, goes up. So it has to be, the level of water here has to be higher than your container. And then you have a bucket here. And first of all, you have to remove the water from here. You suck the water out like exactly like the straw, and then the water is gonna start to flow. Because the water can push up to 10 meters, remember? As long as on the other side, to begin with, you're gonna have you make the vacuum first, right? So once you have the vacuum, then the water it will be able to push out, right? So you're gonna fill your container there. Okay, and so we can apply Bernoulli. We can use Bernoulli here, so that will be your atmospheric pressure. And now that it starts flowing, when it starts flowing here, also you have the atmospheric pressure pushing in this direction. And you also have the water there. Okay, so that pressure is able to push the water up, and then you have all that potential energy here turning into kinetic energy. So that's what is really happening here. It's just potential energy turning into kinetic energy. But first, to start the flow, you need to suck the air out at one end of the tube. Make sure not to swallow the dirty water, of course. And then you can apply Bernoulli, right? So you're going to go on that side, which is the atmospheric pressure, so P1 plus, and then P1 is here. Do you remember it's only the level that matters, so P1, okay, at that level here. Okay, so that level is going to be at that height here. That's a H. So P1 plus rho GH, okay? And here the water is not moving to begin with, and then it's going to move in this direction. So here at that point the water is not moving, or if it's moving it's nothing compared to here. So let's say there is no potential energy. So I'm starting from here, okay, from that part of the aquarium. So you have P1, that will be the atmospheric pressure, and the height is above the ground. So here I have potential energy equals 0. So rho GH plus kinetic energy is 0. It's going to be at that end here. You're going to have the same pressure because it's open to the air, plus potential energy is 0, and here you have kinetic energy. So again, what's really happening is that starting from here, all that potential energy per cubic meter, okay, or per unit volume, is going to turn into kinetic energy. The pressure here will be the same as the pressure there, so it's not really doing any work. It gets it to here, and then what matters is really between here and there. Okay, so you just apply the equation, So now you can cross out the pressure here. I'm going to lose density here. So you're going to have V squared equals 2GH. And that should remind you from physics 1, when you have a load here, a mass M in free fall, before it hits the ground, you're going to have that velocity here. So it's kind of same thing. Once it gets to here, at that point there, you know, it's gonna go. You can think of the equation between that moment here, where the pressure is still, because it only depends on the height here. So at that height, it's still the atmospheric pressure, and that moment there, you see it has gravitational potential energy because it's above the ground. It's going to speed up, and then it's going to have kinetic energy. Okay. And here, you know, it's you cannot go too high, you cannot go above 10 meters, but of course you're not going to go above 10 meters. So anyway, so the final speed is going to be 2GH. So that happens when only potential energy is turned into kinetic energy, and you don't have no differential in pressure. Like unlike when you use a straw. When you use a straw here, the pressure was 0 because you take the air out, and the atmospheric pressure was doing the work. Okay, so that's another example. And do remember that the pressure only depends of the height here. Okay, so the pressure inside here will be equals to the pressure inside there, which is the atmospheric pressure. And it's like a pressure inside. Okay, is it recording? Okay, and then I want to talk about the equation of continuity, and then I will take another example of Bernoulli. So let's say you have a pipe here, and the pipe gets smaller. Okay, so the fluid is flowing. So you have fluid flowing in there from that section here to that section there. And if it's a steady flow, you're going to have always the same amount. So during the same amount of time, you're going to have the same. So let's look at that unit of fluid moving, right? So it's moving during a given time. So during a given time, that much of fluid is going to go through this area. So I'm going to call that the area A1. That fluid here is moving at a speed v1, and it's flowing during a time delta t. Okay, so it's a mass of fluid going through, let's say, this area A1, and I'm monitoring. I take my stopwatch here, and during delta t, I see that much of fluid is going through that cross section. Now I'm located here now, and I find out that if it's a steady flow, of course, during the same time delta t, if you have no leak, if nothing is lost, right? If there is no viscosity, so of course you're going to have the same amount of fluid going through the cross section A2 during that same time delta t, right? So the only way that can happen is that fluid has to move faster. So it means when you have something, a wide pipe, and it gets narrow here in a smaller pipe here, more narrow pipe. So of course the narrow pipe here, where the fluid going through that part here has to speed up. So here you can have the speed V2 and here you can have a speed V1. Does it make sense? Okay, so if you are standing here, you are looking at the amount of fluid going through that cross section here. It's going to be the same amount of fluid going through the cross section A1 as long as the time is going to be the same. Okay, so that volume of fluid, so remember volume, it's going to be the area times area times that height here. I'm going to call that delta x. Okay, it's delta x. So the rate, the volume rate is going to be the volume divided by the time. So how much volume of fluid is going to go through this area per unit second? All you have to do is to divide by delta t. So that's going to be a delta x over delta t is the speed. It's going to be a times the speed. Okay, so that's going to be the volume rate. Okay, so how much fluid in cubic meters is flowing through that area in 1 second. And this amount here has to be equal to this amount there. So that means A1 V1 has to be equal to A2 V2. And if A2 is smaller than A1, that means that V2 is greater than V1. And there is nothing surprising about that. You all know that. You all have played with horses. For example, here you see that if you pinch here, okay, you make it the opening smaller, so the area gets smaller. You see that the flow is going to go faster. If you open here, it's going to go slower, right? So here they define that as the mass flow rate, but you can also define the volume rate. You know, what's the volume flowing through the pipe per unit second? That's going to be A1 V1, and this is called the continuity equation because there is conservation of mass or conservation of volume. Okay, so that's a volume, and you remember that rho equals mass divided by the volume. Okay, so if I multiply the volume by rho, I have the mass. So I can multiply by rho here. I can have rho 1 and rho 2. That means that the mass here, the total mass here, will be the same as the total mass there. Okay, so you have conservation of mass flow. But I'm going to use only this equation here because the density we said stays the same. Okay, we are not we are using only the same fluid. Okay, so that's going to be useful. So this has a very weird consequence. So you agree with me that if the pipe gets smaller and here it's wide, the fluid has to move faster to catch up, right? So that means what? So that means that, let's say you have a wide pipe going into a small pipe and you're going to have fluid flowing here. So you're going to have something very non-intuitive happening. So here the velocity is small and here the velocity is big. So what does it mean? It means that, let's say you have imagine you take a piece of fluid here, so it's going to go from here and it's going to go there and it's going to speed up, right? So if it's speeding up, it means that the work has been done on it. Okay, some work has been done on that unit of fluid. Okay, because it's gaining kinetic energy, and kinetic energy is gained only if work is done. Where work comes from? It comes from the pressure, right? Pressure is the force per unit area. So that means here you have a pressure P1, and inside the fluid the pressure is P1, and inside the fluid the pressure is P2. So which one is greatest, P1 or P2? Because you see here V1 is smaller than V2. So the only way it can happen is that if P1 is greater than P2. Okay, so you can see it as Newton's second law. Remember that force equals ma, and since v2 is greater v1, that means you have an acceleration. Okay, so that means here, if you are looking at that fluid here that is about to enter that narrow pipe, you see that it's experiencing a net force going in this direction, right? So it means you have more force in this direction than you have in that direction. Okay, because you are accelerating. So that means that P1 has to be greater than P2. Or you can say that P1, will explain the work done on this, right? So the kinetic energy gained by this one is explained by P1. So remember the conservation of energy, P1 plus kinetic energy rho 1/2 rho V1 square equals P2 plus 1/2 rho V2 square. Okay, so if you have a gain in kinetic energy, it has to be done at the expense of P2. So P2 is smaller than P1. So that's non-intuitive because it says each time a fluid is moving faster, its internal pressure will be smaller. Okay, so this is absolutely not intuitive, and I will give a lot of examples for you to understand. But anyway, when a fluid is moving faster, its internal pressure, which is energy per unit volume, it's an internal energy, will be smaller compared to here because you have to push it. Okay, so last example, in the case where you have a tube here, so you have a pipe and the pipe is making something like this, so it's going to go up. And let's say you have a steady flow, it's moving here, and you see here it's gaining, there is a gain of potential energy, then it's flowing there. So of course, again here, if you have P1 here and you have P2 there, just by asking your gut, it makes sense that P1 is greater than P2 because it's going to gain potential energy, gravitational potential energy at the expense of the pressure. Or you can think that the pressure, if you think of a volume here of fluid, it's gaining potential energy. Okay, and that's because work has been done on it because of that pressure here, and pressure is just a force per unit second. So you have more force in this direction than you have force in this direction, right? So there is a net force to the right. And then we talked about that already, and we already know that at the bottom the pressure is always higher. Okay, so it's kind of when we look in a fluid here and we talk how the pressure at the bottom here is greater than the pressure at the top. So you have a net force up, that will be the buoyant force, kind of the same thing here. So kinetic energy, conservation of energy, it's going to have P1. So let's say the potential energy here is 0, okay, plus 1/2 rho, maybe the flow is steady, so it's going to be the same kinetic energy. It's going to be P2 plus rho GH, right? And the same kinetic energy, maybe it's not gaining kinetic energy, so I can take that out. And again, we can have that delta P equals rho G delta H. That we already knew. Okay, so that was Bernoulli in a nutshell. Okay, so let's look at the slide now. I hope I'm not taking too much time. Okay, so let's look at the slide here. Fluid in motion. So we are only considering steady flow. We are not looking at turbulence flow, it's another topic. And we are only looking at incompressible fluid, so it means the density is constant. Okay, if it's compressible, that means you can change the density. Okay, so if you make it if you can compress a volume, you are changing it. You are compressing a fluid, you are changing its volume, so you are changing the density. We also say that it's non-viscous. Yes, you are not losing energy to friction, so we call that an ideal fluid. So this is called a streamline. Okay, so it's kind of when we talked about the fields, electric field, gravitational field, you know, we were making those contour lines. So here it's kind of the same. We are looking at the streamlines. Okay, we can even visualize the streamlines with dye and smoke. So here they are looking at the aerodynamic of a car. So I guess the airflow is going here, and you see when the lines here are close to each other, that means it's moving faster. The fluid is spinning up. And when the lines are more spread out, it means the fluid is moving slower. Okay, so it's kind of the contour lines. So here too, you can see, you can visualize the fluid here. You can do that with dye as well. So those are called here streamlines, and you can visualize them. So we talk about that. So this is called the equation of continuity. So it means if it's a steady flow and if the density stays the same, so that amount of fluid here going through that cross section during a given time will be the same as this amount of fluid going through that cross section during the same time. And of course, if you go from wide to narrow, the fluid has to speed up, okay, to make sure that will be that quantity will be the same as this one. So that will be the equation that you are using, okay? So they call that Q, the volume rate. So the volume rate, A, the area times the speed of the fluid is the volume rate. Okay, we just discussed that before. Okay, so let's do a quick example. So if it's unobstructed, so of course it's going to flow slow compared to obstructed, so it's going to go faster. Okay, so let's try to answer this question here. Oops. So we have that Q, that will be the volume of fluid per unit second. Okay, so if I have a stopwatch here, for 1 second, I can measure how much fluid here I'm collecting in a bucket, right? So how much fluid goes through that cross section here. And that will be also the area times the speed. Okay. So here we have the area equals 2.85 times 10 to the negative 5 meters squared. And the rate at which it's filling the bucket, so that's going to be Q. It has a volume of 8 times 10 to the negative 3 in a time of 30 seconds. So you can do that computation. That's going to be 2.7 times 10 to the negative 4 cubic meters in second, right? So in 1 second, I'm going to get that much of volume. Okay, it's a rate. A rate is the amount of fluid in 1 second. And that rate, so 2.7 times 10 to the negative 4, it's the same thing as the area times the speed. Okay, so 2.7 times 10 to the negative 4 equals the area, which is 2.85 times 10 to the negative 4 times the speed. You can cross that out, so the speed equals 2.7 divided by 2.85, and you get 0.95 meter per second. Okay, so Q is a rate. Now, if you pinch it, so you make it more narrow, right? You make it a smaller area here, A2. Okay, so it's going to move faster. And because the area is divided by 2, so the speed is going to be multiplied by 2. So it's going to be 0.95 times 2. Okay, because you have A1 V1 equals A2 V2. And it has to be the same amount of fluid here than it is here. Because it goes like this, right? So you have a wide, and then this is obstructed, and here you have smaller. So here it's going to move faster, V2, V1. So if that area is divided by 2, this one has to be multiplied by 2. Okay? Okay, so let's take, I think there is another example, or more slides. Let's see what we have here. Yes, another example. So here you have a river, upstate New York, Housable River, and that river goes into the Lake Champlain. But before getting to the Lake Champlain, it goes through gorge, right? So it's going to move very fast. And they want you to use the previous, so it comes from Pearson, the previous example, the previous equation, the equation of continuity, to find how fast, no, we know how fast, but how deep the gorge is, right? So you know how fast it's going. So I'm not sure how to draw that. I'm gonna try. So of course you should pause the video and try. I'm gonna do it like so you have like a river. Okay, so this is your wide river. So you have 40 meter wide, and there it's not that deep, it's only 2 meters. And then it gets narrow, really narrow, really narrow. How narrow? It goes to 3.7 meter, and we don't know what's going to happen to the depth. Maybe it's going to be really deep. I don't know. We're going to find out. Right? And that's water flowing. So the water is flowing here. So it's quite slow here. It's 4 meters per second. And here the flow increases 6 meters per second. But we say that it's a steady flow. So you're going to still have, if you have a cross section, so if you put a cross section here, right, compared to a cross section there, you're going to have the same amount of water flowing for that cross section that you have here for that cross section there. Okay, there is a continuity, because otherwise that will mean that the river is leaking somewhere. So you're going to have A1, the speed V1, equals A2, the speed V2. That's going to be the height here, H, and this here is 3.7 meters. Okay, so if you have your stopwatch here, during 1 second, you're going to see flowing a given volume. And now if you are standing here, during that 1 second, you're going to see flow the same volume. Which makes sense? And the volume is A1 V1 for 1 second, right? So A1 is this area here, which is 40 times 2 times V1, it's the speed, so it's going to be 4 equals 3.7 times area, so 3.7 times the height times 6. Okay, so you are solving for H, and I did that for you to go faster. You can pause the video, and I found 14 meters, and that goes 47 feet. Okay, it comes from a book by Pearson. Okay. So another slide. So we did that example here. So Bernoulli equation. Okay, so what you have to understand is that when we talk about pressure, you could find the pressure with a gauge, right? So when you go from wide to narrow, the pressure inside is going to decrease even though the speed is going to increase. And here the pressure is high and here the pressure is low, because you are gaining potential energy at the expense of the pressure. Here you are gaining kinetic energy at the expense of pressure, right? And you can do the math, and that's going to be Bernoulli equation. So those slides come from Johnson and Cutnell College Physics, right? So that's a drawing by Paul Hewitt. Also Pearson, publisher is Pearson Conceptual Physics. And you see that the bubble here gets wider if it's a bubbling water. You can, I'm sure you can come up with an experiment to do that, right? You have a steady flow, but here the bubble are smaller and here the bubble are bigger. They expand. Why are they expanding? It's because the pressure here is lower than here. And it's a very nice drawing, I think, because here you see the streamlines are closer to each other, and here they are farther apart. And that reminds me of the example with the divers. When the divers are at deep in the ocean, they are breathing high pressure air, and the nitrogen goes into the bloodstream, right? But then when they go up, the pressure is decreasing. If they go up to the surface too quickly, you see that the nitrogen here is going to turn into gas and makes bubble because the pressure here is lower, right? So lower pressure, higher velocity. So it's not that obvious. You can experience that when you have a big river like upstate New York going into a narrower river. You see the flow is going to increase, and you can see the streamlines getting closer to each other. Streamline is just showing you the motion of water particles. So you can see that the speed here increases. Okay, so you have a lot of application that comes from a YouTube video. I recommend you to watch. The link is further down. So here you have a burner, Bunsen burner, and the way it works is when you turn on the gas, so the gas is going to flow really quickly. So the flow is gonna the speed is going to be big, and because the speed is big, the pressure inside that gas is low. You open here on the side the opening for the air. Air has a higher pressure. This is low pressure, so the air is going to rush in, and that way you have a complete combustion. Okay, so here you see you have a low pressure here, and of course that low pressure here is going to turn into a high pressure there when the speed is when it stops. So you see you have a fluid moving here really fast, and then here the fluid is stopped, right? So here you have no more speed, or the speed is very slow, like the speed is zero. Okay, so you have lost all your kinetic energy. So all the kinetic energy is lost, so all the energy is going to be into the pressure. Here you have high kinetic energy, so all the energy is in the kinetic energy in the motion, so you're going to have low pressure. So low pressure, high kinetic energy equals to low kinetic energy, high pressure. Okay, so it's very interesting. Okay, so a lot of application here. You can explain the lift, for example. That's one way to explain the lift of an airplane. You see the air here has to move faster to catch up the air from above, because of course you have a continuity of flow, so the same amount of air flowing through a cross section here will be the same as during the same time the air flowing through that cross section. So the air here has to flow faster. That's why you have the streamline close to each other. So it means here you have low pressure, so it means here you have high pressure, and that will provide the lift. Okay, or you can also explain using Newton's third law. If you remember from physics 1, you can say is that you see that the airplane makes the air going down, is deflecting the air down. Okay, so the airplane is applying a force down on the air, so the air is applying a force up. Yes, you can use Bernoulli, or you can use Newton's third law. Here it's a fun experiment to do. You know, you have air blowing here, and you have a ping pong ball. So the air will flow in this direction and that direction. So you're going to have very low pressure here, low pressure here. So the ping pong is not going to fall, even though you flip it vertically, because they have high pressure here, high pressure there. So low pressure on the side, high pressure on the side. Same thing here. When I was a kid, I had that. So you have air flowing, going really fast. So it's going to go this way, and the air fast is going to go that way. So here you have low pressure, but outside you have high pressure. So the high pressure is pushing. So even though you can go sideways, the ping pong is going to go there. You can do this. You can take a piece of paper, you blow above. So that's going to be low pressure here. So high pressure is going to push underneath. It's kind of the lift here. So you're gonna the paper is going to go up. Example also of a perfume. So here what's going to happen is the air pressure here is pushing the things. Here you have low pressure here and you have high pressure there. Okay, so high pressure from the atmosphere and low pressure when it's moving fast. And what else? Okay, so here dangerous situation, especially in Florida when you have a hurricane. If you don't open any window, you're gonna have a higher pressure inside that you have outside because the wind is blowing. Okay, so because the air is moving really fast, you're going to have low pressure here and you have high pressure inside. So the roof can be lifted up, tear up, right? Because it's from the pressure inside being higher than the pressure outside. Here's another example that you can do. You can blow between two paper. So the flow here, that's going to be low pressure, and from outside it's going to be high pressure. So the piece of paper are going to come together. This is the example of the perfume. Again, you are blowing air here, so that will be low pressure. That from the atmospheric pressure, it's going to push the liquid or the perfume up. Because air or liquid or gas always goes from high pressure to low pressure. So here, this is a dangerous situation. It can happen when you have two trucks passing each other. So in between, the air is going to go fast. So outside, it's going to be low pressure, high pressure. So high pressure to low pressure, you can bring the two trucks together or bring those two boats together and they can collide, right? Maybe I will finish tomorrow, or maybe not. I'm almost done. So here you can explain also why those things are bulging. If you are going fast, the air is moving above the truck, so it's going to go low pressure. Inside you have high pressure, so the high pressure is moving that thing up, right? So it's like the houses in a hurricane. So that's going to be the lift. Okay, you have many applications. So for example, here, that's what we can use to measure the flow of air. So it's called the Venturi meter, the speed of air. So what's happening here, you have high pressure, low speed, and then the gas or the fluid is going to go into that tube where you have high speed, low pressure. So if you make two openings here with water inside, you see that the pressure here will be higher than there. And by measuring that height between here and there, you can find the pressure difference and you can find the difference in velocity. Okay, in the difference between this velocity and that velocity. Okay, this is called the Venturi meter. Usually when you have a good plumbing system, you want to make sure you have a connection with the outside. It's called a vent, because here you're going to have low pressure, high pressure. So the air from the outside is going to make sure that the sewage or the dirty water is going to go keep going in this direction, not going back to your house. That will be bad, right? You can also explain the spinning ball and curving ball. So here, and if you make a ball spin, right? So what's going to happen? Here it's going to be faster air, slower air. Faster air means low pressure, high pressure. So the ball is going to be deflected in this direction. Okay. So this is another application, and we have seen that before. So that's just the application when you have the difference in height will turn into kinetic energy. Okay, so remember P1 plus rho GH1 plus no speed equals P1 again, because this is the atmospheric pressure, rho plus rho GH2 plus 1/2 rho V square. Okay, I've done that, and we discussed that already before. Right, so here you have almost no kinetic energy, and then it's gonna the fluid is gonna move faster. That's why the streamlines are getting close to each other. Here you have an atmospheric pressure because it's open to the air, plus you have some kinetic energy, and you have no potential energy. Okay, and here you have the same pressure, no kinetic energy relative to here. Maybe it's moving, but you see how the streamlines are away from each other. Plus you have potential energy, so rho GH, and they're going to be equal to each other, so you can isolate V. Okay, and that could be used to find the speed here in the beer barrel here. And so if you have the speed, you have the volume rate, which is the cross section here times the speed. Okay, so you can know how much beer per second you can get. Maybe you're gonna find out how many cans of beer you can fill up. Okay, so you have a lot of similar application. So that's the math. So this is similar to that idea here. I don't know where it is. This one. Okay, it's kind of the same idea. So this is something you attach on the plane here on the fuselage. So you see the plane here on the side, you have this little thing here, and that's to measure the speed of the plane. So the plane is going in this direction, let's say to the right. So the plane is moving in this direction. Let's say it's moving in this direction. So the air is moving in that direction relative to the plane. And we want to know what's the air flow, how fast the air is flowing. That will be how fast the airplane is flowing. Okay. So we have here a gauge, a pressure gauge, to find the difference between A and B. So you see the fluid here is going inside A, inside that cross section, and it's moving really fast. So you expect a higher pressure. And here we stop the it's like the hose, and you are using your hose to water your plant, right? So here the air is totally stopped at B. So here you're going to have a high pressure and no speed. Okay, so we go back to the example, the previous example. If you want to make a joke, depending on the sense of humor of your friend, this is high speed, low pressure, and then here it's no speed, so it's the water keep moving. All the kinetic energy has been turned into pressure, right? Applying a force on a unit area. So that's the idea here. So let's do the computation. So what do they want? The speed. So the speed, it means the speed that you have here, because here you have no speed. Okay, so that's also an example. So you can stop. You can stop the. You can stop the videos. You have the A and you have B, right? So the pressure A is going to be low. but it has kinetic energy. And we are not going to consider the difference in height, and it's going to be in pressure B, which is really high, but there is no more kinetic energy. So that's going to be 0, right? So PB is higher than PA, so PB minus PA equals 1/2 rho V squared. So it's an example when all the potential difference is going to go into kinetic energy, right? Okay, and the difference in potential in the pressure we have, so 10 times 10 to the third equals 1/2. The density is 0.41 and the speed square. Okay, so you can solve for V and you find V equals 271 meters per second. Okay, so that was interesting. Okay, so that's for people in health. So what's happening here is that when you have some clot here, clotting like fat, and so this is obstructed, so the blood is going to move faster here than it is moving there. So here you're going to have a lower area, lower pressure, and here you're going to have a higher pressure. And the idea is to find, and that comes from the book from Pearson. It's called Physics, Calculus-Based Physics by Wolfson. So what do they want? Okay, they want to find the pressure here, stenosis, and the artery here is clogged. Okay, so it works like a pipe, right? So you have a wide pipe and a narrow pipe, and the streamlines are close to each other, and here they are away from each other. Okay, so why don't you try to do that? It's just algebra. Okay, so we can do two, and you have to use also the equation of continuity. So you have to write A0, the speed here, so the cross section A times the speed here. So here you have a speed V0, and here you have a here you have a speed V, and here the speed V is bigger, larger than V0. So we are not interested in V. We want to get rid of that because we just want the expression for P. And then you have Bernoulli equation, which that says that here you're going to have P P0 plus 1/2 rho. So that will be your kinetic energy. And here you have P plus 1/2 V squared. But you don't want V. You're going to get rid of V using that equation here. A0 over A times V0, right? So you're going to have, so the pressure here is lower than the pressure there. So you're going to have P, it's very hard to write, 1/2 rho V0 square equals P plus 1/2. So I'm square it here. Okay, so I'm isolating P. So P equals P0 plus V0 square, and I forgot the rho. You can do the algebra. Okay, I'm placing that term on the other side. Okay, so I have a half, a rho, and here I have a 1 minus a0 square plus over a0. Okay, let's see if I didn't forget anything. Okay, that's not bad. Right? Now I can put a minus here if I want, so P equals P0 minus V0 square rho 2. Then I have okay, and I have this nice relationship. Okay, so that was not that bad. And here you have exactly the same thing here. So you have also the same equation. So that comes from that video here that I highly recommend you to read. So I had to hurry up because I wanted to finish that before the end of the semester. So, but you can contact me if you have any question. And then the next part of your book will be about viscous flow. So I'm skipping that. You have to fix the Bernoulli equation. It's just like equations. It's not that hard. Viscous means